go. Thanks very much for the introduction and the invitation to talk. Just checking you can hear me and see the slide. Okay, super. Well, thank you very much. It's a pleasure to be, I would like to say here, but actually I'd much prefer to be there and visiting you in person. Today we'll have to make do with online, but I do hope the opportunity to visit comes up in future. And I'm going to talk today, as the title suggests, about both some experimental aspects of gravitational wave detection and some of the astrophysics and the science that has come from our detections, because both of those, I think, are interesting physics, and both of them are ongoing areas of research. You'll see a number of logos on the slides. And up front, I should say the things that I'm going to talk about today are, of course, the work of many people in the LIGO scientific collaboration, the Virgo collaboration, and our colleagues in Japan, the Kagra collaboration too. And actually, I'll mention another couple of potential new observatories towards the end. So this is the work of many, many, many people. I'll give you a bit of a reminder as to the nature of what gravitational waves are. Some of you will no doubt be very familiar, but there may be some new folks who are not so familiar with the field, so I won't make the assumption that you all know. So I'll talk a little bit about that, a little bit about the observatories, tell you where we are in terms of results, bring you up to date, and then a little bit about the near future, because there are some quite firm plans for the sort of next 5 years or so in terms of what the field is aiming to do in terms of detector upgrades and future runs. And then a bit of a further look to the future about the opportunities that there still are for gravitational wave detection and what we're thinking there. So as promised, again, a bit of background. Everyone, I think, is familiar with thinking about gravity in terms of Newton's theory of gravity. It's a fine theory. We are taught it as undergraduates, and it works exceedingly well. And it's still of particular use for many calculations in terms of trajectories and how objects move under gravity, again, in a large variety of circumstances. And it's quite simple. You'll remember Newton's theory says gravity is a force between objects, between masses, and the strength of that attractive force depends on the masses, the two masses involved, and their separation. And so it works exceedingly well, but it does have this uncomfortable feature that it depends on that separation of the objects. And so if the separation of two objects changes, the strength of the gravitational attraction changes, and it changes instantly in Newton's theory. So that means no matter how far apart two objects are, if one of them moves, the other would know about it through a change in the gravitational pull that it experiences, and that feels very uncomfortable. And in fact, it took Einstein to come along and his theory of special relativity, his special theory of relativity, tells us that no information can be transmitted faster of the speed of light, and that includes gravitational information. In other words, special relativity tells us there must be traveling gravitational information, gravitational radiation. The general theory of relativity then describes in mathematical detail how that works, again, how matter, mass, changes the curvature of space-time around it, and how the curvature of space-time tells objects how to move. And in general relativity, that curvature of space-time caused by the presence of mass, we can think of as gravity. And so in our toy model here, the universe, if it had no mass in it, would be that flat rubber sheet. The grid that you can see there would be evenly spaced, all its points. If we add some mass to our universe, it curves its space-time around it in this model. Distances are changed. And that curvature we can think of as gravity. If we stuck a second object down on a rubber sheet there, it would create its own dent. If it was a little bit lighter than our first object, in fact, they would try and roll together. So that curvature causing them to move, that curvature in this model being gravity. And so that's how we're going to we're going to think about gravity today. To give you a picture then of what gravitational waves are, if we think of our toy model here and our objects move on that rubber sheet, as they move, the curvature of space-time around them changes. So that stretching, that flexing of space-time changes. It can propagate across the rubber sheet, our rubber universe there, and that changing curvature, the stretching and flexing of space-time, are what we call gravitational waves. So to visualize that, imagine we've got a tube of space-time. We've just marked a tube in space-time. A gravitational wave traveling down the middle of this tube, in the direction down the middle of this tube, would cause distances to distort, and they distort here, you can see, in a very characteristic way. If we look at the end of our tube here, they're first of all stretched in one direction and simultaneously compressed in an orthogonal direction, and then that oscillates back and forward. We get this oscillating, stretching and compressing of distances at right angles to one another. Very characteristic, and that's what general relativity predicts. Again, to put it on a more formal footing, we say the field equations of general relativity have wave solutions. They are produced when we have some mass that rapidly changes its configuration, it distorts in some way. These wave solutions, these gravitational waves, are predicted to travel away from their source, whatever's producing them, at the speed of light. That's a prediction of GR. And they have a physical effect, which is to change the effective distance between inertial points, markers in space. They physically change that, and they change it in this very characteristic way, transverse to the direction of travel. And so for a bit of an easier visualization, if you imagine a gravitational wave traveling into the board here, into your screens, it would do what that little circle's doing. That's sort of the end of our tube here, stretch distances in one direction, simultaneously compress them in another, and it would oscillate back and forward. And that's the physical effect that we measure. To do that, to make physical observations, there's an instrument that is ideally configured to do that, which again you'll recognize from undergraduate lab classes, and that's a Michelson type interferometer. So here we've got light from a laser, we shine it on a beam splitter, splits the beam into two beams at right angles to one another. We place mirrors down, and you can see our mirrors here. Those are our inertial markers. You can imagine them as the dots at the top and the side of our circle here. A passing gravitational wave, again, in this case coming down into the detector, would stretch one arm and simultaneously compress the other. And that would oscillate. And so as we look at the output of our interferometer here, the paths that light has traveled in each of the arms changes. And so when we look with a photodetector at the output, the interference fringes, the bright and dark spot that we can see of the detector changes. So by measuring the change in intensity at the output of the instrument, we can sense the motion of those mirrors and try and sense the passage of a gravitational wave. Now, the challenge is that gravitational waves do not have large amplitudes. The effects we're looking for are very small, and we can quantify that. If we say the initial length of one of these arms in our Michelson is some distance L, passing gravitational wave stretches or compresses it by some amount delta L, where the size of the gravitational wave here we call h, and we can calculate from general relativity for typical big astrophysical objects out there in the universe what GR would suggest the size of their gravitational wave amplitude would be. Turns out to be about 10 to the minus 22. So h we can calculate. If we just rearrange our expression here and we define h again in terms of the strength of this effect, it's 2 delta L over L. That means the motion of a mirror, the movement of a mirror that we're trying to detect here becomes h upon 2 times L here. if we then put in some numbers, we know h is about 10 to the minus 22. If we make a 1 meter arm interferometer, so we stick it in a tabletop, then that means we'd be trying to measure changes in the position of these mirrors of about 10 to the minus 22 meters, which is exceedingly small. But what this tells us is if we make L large, then for the same h, the effect that we want to measure, the delta L, it becomes larger. And so that's what we do. We don't build 1 meter interferometers. These are not tabletop devices. We make L kilometer scale, and that enhances the signal size that we're trying to detect. So what sort of sources produce gravitational waves that we can measure? Well, the now classic example is merging black holes, and you can see a little animation here. 2 black holes with the colors underneath sort of representing the distortion of space-time. As this is a binary, so binary system, they're caught in one another's gravity, spiraling round, radiating and losing energy in the form of gravitational waves as they do so. Losing energy, they're getting closer and closer together, so their orbit speeds up. The amplitude of the gravitational waves, in fact, gets larger as they get closer and closer together until eventually the 2 black holes merge. The amplitude of radiated gravitational waves peaks, and a new black hole is formed on their merger, which then again oscillates a little bit and sends out that traveling distortion of space-time, that gravitational wave, out across the universe, predicted by GR to travel at the speed of light. So I will play that animation just one more time, because underneath you can see a very characteristic waveform. And that is telling us if you're on the surface of that gravitational wave arriving, you can think of that waveform underneath as telling us about the oscillation of the mirrors in our observatory and our gravitational wave detector. So their positions oscillate back and forward, and the frequency of that oscillation increases again as the gravitational waveform evolves through, passes through the mirrors. They shake faster and faster. They eventually reach a peak in their displacement, again, which is telling us about what's happened when the black holes merge, and then that oscillation settles down. So it's a very characteristic signal that we look for this from this particular source. And indeed, that kind of signal is the signal that was the first detection, again, made back in September 2015, reported in February 2016. And you can see on the top here the data from the paper from one observatory located in Hanford in Washington in the US, the other one in Livingston, Louisiana, and you see this characteristic oscillation of increasing size, increasing frequency in both instruments, again, which matches very nicely. And there's a few things to note here. One, this is over quite quickly, and this is time in seconds along the bottom here. So this is all over in half a second. This wave has flashed through the detectors for this particular source. That frequency evolution and the size of the signals has embedded in it the characteristics of what produces it. So that's what allows us to do the astrophysics. And so from that, we can extract information about the source. We can tell it was 2 black holes. We can tell that they collided about 1.3 billion light years away. We can tell the final black hole that was formed in the merger was about the size of Iceland, spinning about 100 times a second. It was about 62 times the mass of our sun. We can actually tell it was probably an oblate spheroid. Again, it was because of the speed of which it was spinning, it was slightly distorted, and all of that information we extract from the shape of this waveform, again, which we have extracted from the movement of our mirrors. So that's the physical process that we go through to get to the properties of our source. And for scale, again, the peak-to-peak motion that we're talking about detecting here was, of the order of 10 to the minus 18 meters. but just a little bit of information about how do we get that out? Where is this information coming from? Well, the phase evolution of the wave tells us about the sort of combined masses and spins associated with the black holes. Partial information about the spin, more information about the spin depending on the sort of any modulation of the amplitude of the signal. The highest frequency telling us about the sizes of the objects just before merger, and again that post-merger signal giving us information about the final black hole. So it's embedded in the signal there. Now, given that we're trying to sense motions of mirrors that are, of order less than 1,000th of the size of a proton, these are challenging experiments to make. I choose diagrams of Michelson interferometers. Of course, the real instrument is somewhat more complicated, and reality kind of goes in this direction of increasing complexity. Just a couple of words then on measurement, because we'll come back to, we'll oscillate ourselves between talking about the instrument and the astrophysics here, because improvements in the instrument translate into improved astrophysics for us, and there's still some way to go. You can imagine in our instrument here, we're trying to measure the motions of the mirrors, remember at the ends of our arms, that many things can in principle and in practice move those mirrors through a displacement larger than a gravitational wave would. So they would mask our signal, they're noise in our instruments. So the obvious one first is seismic noise. If we just took our observatory and we just sat the mirrors on the ground or on a table, ground motion would cause the mirrors to shake. That turns out to be, in relative terms, easy to isolate against. We suspend our mirrors, we hang them, and that forms a mechanical filter. The initial observatories just used wires to suspend the mirrors as pendulums to isolate against ground motion. There's intrinsic thermal noise. These are mirrors, they're made of fused silica, pure glass. Every atom and molecule there has some thermal energy, so it's each atom and molecule is vibrating away. These are all coupled in the mirrors, but that thermal energy then eventually turns into motion of the front face of the mirror, so at a level that we have to care about. These are giant quantum measurement devices. We're using light as our probe to sense the motion of the mirrors. And we're detecting that light using a photodiode. So the inherent nature of light gives us some noise sources. Every time, so we can talk about light as waves or photons, we talk about both. Every photon of light that bounces off the front face of one of our suspended mirrors transfers some momentum to that mirror. It causes the mirror to shake as the photons rattle off it. The more laser power we use, the more photons there are shaking the mirror, so that noise source gets worse. On the other hand, we are sensing our signal at the output of the observatory using a photodiode. Look at the light coming out. So there's photoelectron shot noise in the detected photocurrent, again, photon counting statistics. The effect of that reduces as we turn up the laser power. So there's kind of two competing noise sources. It turns out at any frequency, there's an optimum light power that balances, that minimizes the combination of these sources. And the limit that sets to measurement of the mirror positions is the same limit you would get if you took the uncertainty principle, delta x, delta p less than or equal to h bar over 2, and applied it to the mirrors. So it's the standard quantum limit. So they're quantum measurement devices. And again, we'll talk a little bit more about that later. Last but not least, there's gravitational gradient noise. At low frequencies, we've happily suspended our mirrors. They're hanging there peacefully, quietly, and we've isolated them from other noise sources, and someone comes and walks past our detector. Well, Newton tells us if you've got two masses and their separation is changing, you've got a change in gravitational pull, and you cannot shield against gravity. And so there are many things that move slowly at low frequencies then that can exert a local pull on our suspended mirrors. They tend to happen slowly, so this is a noise source at low frequencies. And it's one of the reasons that for lower frequency detectors, we think to put detectors in space. So all of these noise sources, again, are kind of thinking of an equivalent delta L of the mirror that they are sort of inducing. It's easy to think about that for seismic and thermal noise. They all, again, are helped if we make the arm lengths larger, again. And all of these give us their own technological and engineering challenges. The embodiment then of these big observatories using these technology, again, there are a number of these around the globe, and I'll talk about various of them, but perhaps in most detail, the LIGO observatories. You can see here's one located in Hanford in the northwest of the US, one in Livingston near Louisiana, operated by Caltech and MIT, but used by, and again, worked on by the LIGO scientific collaboration I mentioned earlier, many scientists internationally. You see the outside, again, with this sort of a concrete beam tube cover. Inside, there's a big vacuum pipe, about 1.2 meters, again, through which our laser beams are fired. And then inside the buildings, again, and the end stations are the various components. I won't talk about this in particular detail. I'll talk only really about one experimental system because it's the one, again, that is closest to my research area, which is in reducing the thermal noise. And actually, thermal noise turns out to be the noise source that limits the detector at its most sensitive frequency band. So here we've got frequency along the bottom. We've got 100 hertz, a kilohertz. So we are looking for signals kind of in the audio band. Up the side here is strain. That's our delta L over L. So it's roughly telling us about the spectral density of the sensitivity of the instrument. And thermal noise is the one that hits us in the most sensitive band. We want to keep that as low as possible, and we do that by using intrinsically low thermal noise materials. So these mirrors that I've talked about are macroscopic. They're 40 kilogram mirrors. There's a sort of one at the bottom of the suspension chain here. It's actually a 4-stage suspension to give us multiple stages of seismic isolation. And then the final stage is a fused silica test mass mirror with a coating on the front to make the mirror suspended in 4 fused silica fibers, because the intrinsic Brownian motion, the energy dissipation is low in fused silica as a material, and that was one of the UK contributions. Right at the bottom, there's one of those 40 kilogram mirrors. These are, again, marvels in themselves. They have to be very low absorption. We use very high laser powers. Again, very carefully coated. Again, I won't talk too much about that, but it's to give you a feel for some of the instrumentation that's in there. LIGO is, of course, only one of it's a pair of observatories in the global network. There's also the LIGO with its 4-kilometer arms. There's also the Virgo Observatory in Europe with 3-kilometer arms, GEO 600 meter arms, a UK-German detector in Hanover. There's the CAGRA instrument, which has 3-kilometer long arms and is in a mine. It's actually underground, Kamioka mine in Japan. And to come, a third LIGO instrument, again, to be located in India. And so why, you might ask, are there so many? Why do we need this network? Well, this is the principle of why, and I'll talk about in practice where that shows up in our observations as we go on. Gravitational wave detectors, unlike telescopes that you point at a particular portion of the sky, these observatories are more like microphones. They have an individual instrument has some sensitivity, kind of almost in all directions, not equal, but in almost all directions. That's both good and bad. I mean, it's good in some ways, but it does mean that with a single instrument, it's quite difficult to get information about where on the sky a signal has come from. And so quite simply, you want multiple instruments. Gravitational waves have a finite travel time. So by timing when gravitational waves arrive at the different observatories in the network, you can deduce directional information about where the signal must have come from. Quite simply, if a signal arrived at the Livingston Observatory first and Hanford a bit later, it's telling you directionally it must have come from somewhere in the south as you look at the sky. And you can quantify for different combinations of instruments and different locations on the globe what the directional accuracy of the network would be. So there were originally actually planned to be 2 instruments at the Hanford site, one at the Livingston site and one at Virgo. If you take that model, what you see here is a sort of representation of the sky opened out and flattened, and the ellipses tell you the accuracy with which we could tell the position of a source coming from that portion of the sky, and the red X's are portions of the sky for which we would have no sensitivity, even with that network set up. So you can see it varies a bit, but there are some portions of the sky where we really wouldn't know terribly well the location accuracy of a source. If you increase the number of detectors, and this is a model where there's one in Hanford, Livingston, there's one in India, Japan, and there's the Virgo instrument, that uncertainty shrinks again, and we are able to determine with greater accuracy where a source in the sky has come from. And that matters for the science that we want to do. To bring us kind of to date, what observing runs have been carried out? Well, we talked about the first detection. Again, there was that binary black hole first detection in 2015, and the first observing run, where there were only the LIGO observatories running, but again, the joint work by the collaborations in making the detection. The second observing run, then Virgo joined O2, again 2017. So that was a particularly productive run. To give you an idea of how well the instruments were operating, there's that design sensitivity curve, frequency, this time displacement. Remember, it's previously it was strain delta L over L. This is displacement, but it's all about movement of those mirrors. That's the design sensitivity for them instruments. For O2, still wasn't quite at design sensitivity. There were still instrumental sort of things not quite complete. Even so, there were a whole number of more binary black hole detections, and again, a quite spectacular detection, this time of 2 neutron stars colliding. So not this time the final endpoint of a stellar collapse that was unconstrained, but neutron stars, of course, being where there's been a stellar collapse that's paused just before the black hole stage. So you'll see we give snappy titles to our detections. GW 170817, what does that mean? Well, GW is this gravitational wave detected on the 17th of August 2017, so it's the date of detection. And that one event, that binary neutron star collision, was the source of a whole bunch of interesting science, a large number of papers. I've just given you the headline summaries here. We detected gravitational waves, but it also, this time, because it wasn't black holes, it had real matter there. It was the source of electromagnetic signals, which were detected across a whole range of wavelengths with a large observing campaign, lots of electromagnetic space and ground-based telescopes involved. Some of those, well, it was picked up actually first in gamma rays, confirmation of the collision of neutron stars as the source of short-haired gamma ray bursts. Because we detected light and gravitational wave signals, we were able to test that prediction of GR to high accuracy, that gravitational waves should travel at the same speed as light. There's about 1.7 second difference in the arrivals, the detected gravitational wave signals and the gamma ray signals, again, which is most likely, I suspect, a real physical effect, but put a phenomenally tight bound on that. Again, just to pick out a couple of others, an independent measure of the Hubble constant, so a gravitational measure. So there was a long-standing sort of paper from Bernard Schutz in Cardiff, who showed that you could get the distance to a gravitational wave source from its signal. That combined with, again, the ability here to have electromagnetic conformation, allowed the calculation of a gravitational probe of the Hubble constant, again, independent of the sort of cosmic distance ladder that's used in other techniques. So again, a really interesting result. And also, again, from the electromagnetic observations, the sort of signals there suggested that these types of collisions, which again are confirmed now as neutron star collisions, to be the source of some of the heavy elements in the universe, in particular platinum, gold, the shiny exciting ones, but also some less shiny exciting ones. But again, I mean, that's why this artist's impression has these lovely gold swirls around the outside. All of that coming from the combined gravitational and electromagnetic observations from this particular event. So again, the second observing run had that in it. And one of the reasons we were able to be efficient at making these was the addition of the Virgo Observatory to the network that allowed a pretty good localization of the source of the signals on the sky, which makes then us able to work with our electromagnetic observer colleagues to allow efficient use of telescopes to pinpoint the right place to look. And so that was a very important development. So the second observing run, also, we've gone from making individual observations to being able to publish a catalogue, again, in quite a short period of time in the field, again, after only a couple of years. And this plot here for you, just to explain what we have here. Up the side is number of times the mass of the sun. So this is stellar masses. And then spread out here, what you can see in blue are the gravitational wave detections of here black hole mergers. Again, so one here about 20, 29, or rather just about over 30 solar masses merging to form a new black hole. And so that's what you're seeing in blue. In purple were the existing results of electromagnetic observations that were consistent with the objects being observed being black holes. Down at the bottom here, you can see again in yellow the neutron stars that were known to exist from electromagnetic observations of isolated neutron stars, and in orange here, that binary neutron star merger, the two neutron stars merging to form, again, a new compact object. So that's after the second observing run. And then if you think back to that run schedule, the observatories were stopped. Again, we stopped observing and actually took a pause between 02 and 03 to improve the sensitivity of the instruments. You'll remember they were not at design sensitivity. I mentioned when we talked about the noise sources earlier that quantum noise is one of the sources of noise here, and that was one of the noise sources that was again addressed by using squeezed light. We also turned up the laser power in the instruments. Those should both help the high frequency sensitivity. Of course, if you turn up the laser power, we said that increases radiation pressure, which starts to sort of push on the test mass. So by improving those things, that meant we had to make some other technical, I won't go through them in detail, but people often say, why don't you just keep running? Again, there's exciting results coming in. It is important that we stop every now and again, make technical adjustments, because we do then improve the sensitivity of the instruments, and we'll see why that matters. There are strong science drivers for doing so. So this plot here, you can see time and days along the bottom, first observing run, second observing run, and the cumulative number of detections or candidate detections up the side, and you can see how that evolved through the first and second observing runs. O3 observing run, which happened to be in 2 parts, you can see the steep increase. So there are strong motivations for improving the sensitivity of the instruments, and every time we do that, we're able to increase the potential number of candidate events. So our latest run then, we're here in 2022, the latest run was O3, this time with LIGO, with Virgo, and with CAGRA just at the end, joining there. And as I say, this was in 2 parts with a break in the middle. Our sort of catalogue of events now looks more like this. You can see, combining everything, we now have quite a large number of events. We've got solar masses up the side here. You'll notice the scale now goes to 200. So we're picking up events that start to get into a very interesting range of intermediate mass black holes. We have more binary neutron star collisions. They also start to, we have neutron star black hole collisions. And again, some interesting events in the middle here, at least this one here, where one of the objects is in what looks often on a plot like this as a gap, a mass gap between neutron stars and the latest black holes. So in total, I think there's about 90 events now. Once you have a large number of events, you start to be able to do different science, to start to look at the statistics of what you have. When we measure the properties of our sources, statistically, that starts to give us information about the likelihood of how these sources may have formed, their formation channels for the binary systems. I will only, again, give you a couple of individual examples of this. Intermediate mass black holes, again, neutron star black hole collisions, and that question of compact objects in the mass gap. So intermediate mass black holes, so what does that mean? Well, there were no prior observations of black holes that had masses in the range about 100 solar masses to about 100,000 solar masses. So stellar mass black holes, below that, yes. Supermassive black holes at the center of galaxies, yes, but this kind of gap. And sort of the underlying theory suggests that you can't form black holes in that range from straight stellar collapse, because of the stellar astrophysics not allowing you to reach the right conditions to then form black holes in that range. So we now have a number of these sorts of detections, but I'm just going to pick one, GW 190521. As a reminder, that just means detected on the 25th of May 2019. So it's one of the ones on that plot, a black hole merger. So we picked up that signal, characteristic signal, where the larger of the 2 black holes was about 85 solar masses, the smaller one about 66. At that point, both of those were more massive than things we had detected to date, and that post-merger black hole about 142 solar masses, so squarely in the intermediate mass black hole range. So it's, again, what are the implications of that? Well, either you can have stars collapse to form those high mass black holes, or it's telling us about the environments in which those black holes, that black hole merger was occurring. Potentially that we have hierarchical mergers, that smaller black holes merging to form slightly larger ones, and so forth, scaling up these sort of black hole sizes. To do that, of course, requires black holes to find one another, to be in environments where there are other black holes nearby, to have these multiple merged events. So possibly it's telling us these are happening in stellar clusters, active galactic nuclei. So the properties themselves start to give us information about the potential environments. Neutron star black hole collision. So again, you'll now recognize the code, 5th of January 2020, and 10 days later, a second event, whose signals were consistent with the compact objects that we're combining being neutron star black hole systems, these were, again, predicted to exist in theory, but I think there was no previous observational convincing evidence of their existence until these detections. So the first one, you can see the components, 8.9 solar masses, black hole, 1.9 neutron star. That was picked up, I think, in 2 detectors only. So again, here's one of our sky location maps, which meant that the accuracy with which we could tell where the signal was coming from was not fantastic. The second one, in 2 LIGO and 1 Virgo instruments. So again, we were able to determine more accurately where it was. In principle, perhaps they could have produced electromagnetic signals. However, remember, we need to know where to point our telescopes. The combination of uncertainty in position and the distance actually out to the sources meant observational light was unlikely, and in fact none was observed, but the first detection of this kind of source. And then lastly, here we've got 140819, 14th of August 2019, a detection with quite unequal masses, you can see. Again, coming from this sort of, one of them coming in this region here between kind of neutron stars and previous observations of black holes. So one of these then squarely in the black hole range, the other sitting in that range somewhere between sort of the heaviest known neutron star and the typical masses of detected black holes. I think we can't say for sure which one it was. There are observations that are consistent with the lighter one being a black hole, but I think we can't completely rule out the neutron star. But again, it's starting to probe an interesting parameter space. The other, again, there's another interesting aspect of this one, that it was used as, again, another different way to extract the Hubble constant, this time without an electromagnetic counterpart, but by probabilistically deciding what the likelihood was of it being in a particular galaxy cluster and extract and weighting the redshifts accordingly. So those are just a few highlights. Again, there's a whole bunch of other stuff that I haven't talked about, but I just picked out a few examples of the sorts of places that the observations are again, still in discovery space and still turning up new astrophysical implications. Where are we now? Well, again, I extracted this from the collaboration web pages as a recent update for the start of the next observing run. Like many other parts of science, the pandemic has induced delays in our schedule. So the plan currently is to start the next observing run in mid-December this year, although of course that still is some time away, so we still need to wait and see. But there is a webinar planned, again, on an update later this month on the status of the detectors and when that next run might start. So that kind of brings us up to date. What's coming next? We've talked a bit about the sort of sensitivity of the instruments, why we keep turning off to upgrade them. But even beyond the design sensitivity of the current detectors, whether it's Advanced LIGO, this happens to be the curve for that, but also Advanced Virgo, we have a fairly good idea of what the limiting noise sources are. And I talked about those earlier, and actually pretty mature plans in place for the next stage of upgrades. Won't talk about this in detail, but just to say this is well underway. Tackling a couple of those noise sources, again, the quantum noise and actually the thermal noise, this time not necessarily from the mirrors, but from the actual coatings, the few micron thick coatings that we put on the front of those test mass mirrors. So that is mature plans for that underway. Eventually, we will, however, hit the limits of the infrastructures. Again, we can know to some extent what those will be from physically the length of the arms, the local seismic and Newtonian noise. There are technical things that we think we know how to do to improve the instruments, but it may not be possible to do it in the existing infrastructures. And that we've known for a long time. And in fact, there's been a lot of work in Europe in looking at conceptual designs for a next generation observatory to make a substantive difference in sensitivity. A factor of 10 in displacement sensitivity beyond the design of the advanced instruments. And that makes a significant difference to the science that can be done. So there was a conceptual design done some time ago in Europe for a potential new European observatory, a paper design study that was updated recently. And work is ongoing, looking actually at some candidate sites, two main candidate sites to host such an instrument, one in Sardinia and one in the sort of Dutch, Belgian, German border in a particular region there. And there's also another third site investigation. And there's considerable work ongoing to look at those. You'll notice these are underground sites. And again, I talked about seismic noise and gravity gradient noise at low frequencies. Actually, it turns out one of the main sources of gravity gradient noise is from the Earth moving. If you put the detectors underground, that actually goes down. So I won't talk in detail, there's a lot of work on that. A parallel effort in the US, where there is a design study just completed around, and actually even slightly bigger. This ET is about 10 kilometers in the US, looking potentially at a 40-kilometer arm length instrument, a slightly different design, but again with around the same goal for sensitivity improvements of a factor of 10. What does that mean, that extra factor of 10? Well, this plot here, don't worry too much about the details, but every little, imagine a cosmology where the Earth is at the center of the universe, that's us in here. As we go outwards, we're looking at the sensitivity increasing of our gravitational wave detectors to pick up gravitational wave events. Every little white dot in here is meant to be a black hole merger. And by the time you get to the sensitivities of the instruments we've talked about, Cosmic Explorer or ET, for kind of stellar mass black holes, the design sensitivity of these instruments would essentially detect them all in the universe, no black hole left behind. So we start to talk about rates of 10 to the 5 binary black holes detected per year, going out now to real cosmological distances, large numbers of binary neutron stars, and you can do, once you have these kinds of numbers, a whole different set of science. It's because you have the statistics. The other thing that you have is high signal to noise ratio. And one of my colleagues now at Penn State, Satya Prakash, I gave a talk at a general relativity meeting, and Satya asked me to impress on people the difference that this makes conceptually in what you can do once you're measuring mergers with phenomenally high signal to noise ratio, that you're no longer just testing general relativity, you're in a regime where, if there are alternative theories of gravity, you want to know what the predictions of those would be for these kinds of strong gravity events, because that's the sort of testing regime that we would be in with these third generation instruments. In fact, everything I've talked about today is only part of the gravitational wave spectrum. We've been talking about ground-based interferometers. There are other sources of gravitational waves, supermassive black hole mergers, again, of black holes in the centers of galaxies, extreme mass ratio in spirals, small black holes circling round, again, huge black holes that would produce signals that we will not be able to detect in the ground-based instruments because their frequencies are such that we would not be sensitive to them. So, of course, there are space-based detectors, LISA, again, planned to fly in the 2030s, aimed at those, pulsar timing, again, CMB experiments looking at other portions of the gravity wave spectrum. So there really is a whole lot of new science still to come out there. just to finish, one thing I would say, because we don't often talk about this, is that R&D we do for the observatories, the technical R&D, is a rich source of spin-offs. And so these are all actually just examples from my own institute in Glasgow, working with colleagues in the biological field, looking at using our understanding of vibrations, again, with Stuart Reid now at Strathclyde and colleagues in stem cell biology in Glasgow, using those vibrational control techniques to selectively turn stem cells into bone, again, for applications there. Working with the data analysis colleagues in Glasgow, working with Optos, company that makes machines to scan the retina to improve the quality control actually of the machines that are produced, again, which eventually turns into an increased number of scans per day that can be done for real people. Again, lastly, again, not this time making large gravity wave detectors, but making small gravitational sensors to measure local changes in gravity here on the surface of the Earth. And Giles Hammond and colleagues in Glasgow are working on that with applications from security and defence to monitoring magma flow. So there's a whole different set of things ongoing there. So to finish, the detection that we talked about is a wonderful achievement. Again, in some ways the end of a long quest to get there, in other ways the beginning of a whole set of different science and gravitational wave astronomy. That R&D that enables it is still ongoing, needed for that next generation, and I'm sure there are more discoveries to come and hopefully a bright future ahead. And I will stop there.
Thanks very much, Sheila, for this wonderful talk. So we'll take some questions. I'll wait for people to raise their hands. Hopefully I can.
Sure.
Chad? You
hello, can you hear me?
Yep.
Yes.
Hello. Thank you very much for the good talk. I just had two quick questions, if that's okay. One was about the naming convention. The naming convention uses the dates, but I just thought, what happens if you have two detections in one day? The other question I had was, you mentioned we use the signal to get a measure for H0. Was there anything interesting from that measure in terms of, did it prefer late universe or early universe value, or was it the error bars were too big?
Sure. So first of all, the naming convention, you are correct, and we started to worry about that a while ago. And it's interesting. It's partly because the field has gone from making a detection to, oh my goodness, what are we going to do when we've got all those events? And so there is actually now a second part to the name that I think has UTC in it. I didn't trouble you with the extra digits here because I felt it's enough to make people look at the long string of numbers, which is just a date. But there is a second part to that now, actually, that has a more precise, accurate time in it. So that copes with that. In terms of H0, I should have put the graph in. So fundamentally, the number the binary neutron star result comes up with is right in the middle between the cosmological measure and the supernova measure. So it doesn't, and sadly, the error bars just cover them both. So it does not distinguish between them from that one measurement. And what we need are a few more measurements with an electromagnetic counterpart, and that then will reduce the error bar. So it will come, but we could do with a few more binary neutron stars with electromagnetic counterparts to get there more quickly. So looking forward to that. So no, we don't solve. We are consistent, sadly, with both at the moment. But that in itself is, again, it's interesting because it's a completely different probe, a gravitational probe. And we could do with it, again, and we also need more telescopes to be able to pick up the electromagnetic signals from events further away, because it will be interesting when we have a set of gravitational wave measurements, again, at different distances to extract the H0 values from those. So yeah, we don't distinguish yet, but we are consistent with the being in the middle of the other two.
Thank you very much.
We have another question. I'll ask one. So I'm quite curious about how sensitivity and number of detectors compete when it comes to localization. So, I mean, if I had very sensitive detectors and I only had 3 basically, but as opposed to adding a couple of more detectors which are not that sensitive, but they do capture, I mean, at least part of the signal, or the loudest part.
So I can't give you a quantitative answer to that, but we have looked at that in excruciating detail actually, and there are a few papers on that. So I don't have an instantaneous answer for you. The answer is, though, you do want multiple instruments, and 2 is not enough. You really want a minimum of 3. I can't give you the quantitative answer, though, although it has been looked at. There have been network analyses done that look at exactly those questions: the orientation of the detectors, the distribution of them on the surface of the Earth, the relative sensitivity to extract that trade-off you talk about.
So let's assume for a moment, let's be optimistic, assume that Einstein telescope and cosmic explorer will turn on at some point. Will LIGO still be relevant for localization for them? I mean, will it still help?
There are different things that you can do with different combinations of advanced and 3G detectors. And it depends if you do have multiple 3G detectors, because as you can imagine, each one is a massive infrastructure, significant investment. So there is a question of how many you believe that you're going to have. So some number of second generation detectors is still relevant, I think, with a third, and it depends exactly what you want to do. So okay, so I'll stop there. Have been some studies done on that. In fact, GWIC, which is the Gravitational Wave International Committee, set up a subgroup to look at the future and to look at the science case for future detectors, and again the distributions and number of these. And so that was, I can't give you a quick answer, but it was studied in detail in there.
Okay, thanks. Claire?
Yeah, hi, thanks. Yeah, I agree. It was a really, really nice talk. I wanted to ask about, you mentioned some really interesting spin out projects, and I just sort of wondered if you could say a little bit about how they came about. Was it sort of serendipitous? It sounded like a couple of them were at Strathclyde, so was that just sort of serendipitous, or yeah, how did that come out of the science
Sure.
for LIGO?
So it's interesting. So I think some of them serendipitous, and other ones we could see that there was going to be potential, and we're still working on potential interest there. So the stem cell one was more serendipitous, and there was I think a serendipitous meeting between a couple of folks, one of which in cell biology and one of which was us in the gravitation. It was just 2 people who knew one another, who realized there could be something interesting there. And so at that point, Stuart Reid was in my group in Glasgow, and it was, I've forgotten his name, a professor in cell biology, and Jim Huff in Glasgow. They started to talk and look at the potential for this, and that one really has grown. Stuart is now, he's actually head of department of biomedical engineering, I think, at Strathclyde. So he left faculty position at UWS, went to Strathclyde. And he's working with Manuel Salmeron Sanchez in engineering in Glasgow. So it's now a cross-institution as well as cross-research area activity. That's been really interesting. They're looking at clinical trials coming up for some of that work. The retinal scans, I confess again, I'm not quite sure where that came about in terms of the specific connection, but we had been motivated, I would say, to try and understand what the wider application from some of the technologies was. I mean, the MEMS one's interesting because that's one that has both kind of a spin-out application, but also relevant applications for us. For some of the gravitational gradient work, it's the local ground motion that actually will determine the level of gravity gradient noise. So being able to measure local ground motion is interesting in itself. But that particular work turns out to have broader engagement. So once we started, and it's Giles Hammond again who'd been looking at that to think about it, it became clearer that there was a gap in the market. So there are very sensitive accelerometers in your iPhone. So that's or your Wii game controller, you know, that tell when you're moving your hand or measure your steps. They're cheap. You make them on a chip. They're very cheap, but they're not that sensitive. Or you can spend, you know, hundreds of thousands of dollars and buy a very sensitive instrument from a commercial geophysics company, but it weighs quite a lot too. So some of the technology in silicon that we were thinking about actually for next generation gravitational wave detector suspensions, Giles and colleagues realized could be miniaturized to make a device that both was sensitive and could be made on a chip. And that makes it very attractive. So there was some serendipity there. And again, I'm working with colleagues in engineering in Glasgow who have the fabrication expertise, Doug Paul and colleagues there. There was, again, a cross-department collaboration that came about. The high precision bonding is something that we actually learned from colleagues at Stanford. So that was serendipitous, and early in my career, I was a visitor at Stanford. There were folks there working on the Gravity Probe B space experiment, which had an all-fused silica telescope, and they needed to find a state of joint-fused silica that was optically transparent and that was suitable for launch. They'd been looking at optical contacting, which can be very strong, but it's quite difficult to tell its reliability. And they actually had developed and patented a technique, simple technique for chemical jointing that was still stable, optically transparent, that we needed because we need to make our all-fused silica suspensions, but you can't put glue in an ultra-high vacuum system. It ruins your mirrors. So we learned it from them, and again, most recently actually been working with a laser group, Ursula Keller's group in Switzerland, applying that technique to some of the stuff that she's been doing in making high-power lasers. So a whole range of different stories there.
Thanks very much. That's really interesting.
Do we have another question for Sheila? Okay, if not, thanks very much again, Sheila, for joining us today and giving this wonderful talk.
My pleasure. It's, as I say, delighted to be able to do so, but one day I hope to be able to do so in person and visit.
Yeah, hopefully next time I'll be able to have you here. That'll be great. Okay, good afternoon to everybody. Thanks very much. Bye-bye.